Satellite data shows steady uplift beneath Columbia River Gorge, hinting at hidden magma activity reshaping the iconic Pacific Northwest terrain.
Along the mist-laden backbone of the Pacific Northwest, where the mighty Columbia River carves its deep passage between ancient cliffs, there lies a restless force beneath the surface, unseen yet undeniably present. Here, dramatic scenery unfolds. Waterfalls cascade from layers of volcanic basalt, forests thrive in perpetual green, and the land itself stands as a living memory of monumental natural forces. But underneath this splendor, beneath these jagged bluffs and emerald canopies, something older stirs, an ongoing transformation now coming into view thanks to 21st century technology. For centuries, the Columbia River Gorge has been celebrated as a natural marvel of erosion, a landscape shaped by the slow persistence of water and the violent episodes of prehistoric floods. Its cliffs, towering as much as 4,000 feet above the river, bear unmistakable scars from glacial outbursts that once scoured the land clean. Even today, the forests recall more recent upsets, catastrophic fires and landslides that periodically clear the growth and rewrite the terrain. Yet, while locals and visitors alike have long marveled at these visible changes, today's scientists are lifting the veil on previously hidden movements. Now, the latest watchmen are not riverboat captains or romantic poets, but satellites high above the atmosphere, unblinking, precise, and capable of capturing the quiet, powerful pulse of this rugged land. Over the past decade, these orbiting sentinels have contributed to efforts by scientists to synthesize structural, geophysical, and topographic data, piecing together a new, evolving story beneath the gorge. Their findings reveal sustained, measurable uplift on a surprising scale, patterns that, when viewed with the depth and breadth granted by modern technology, suggest more than erosion or slow tectonic drift at work. The ground is indeed rising, quietly but persistently, across a landscape that once seemed immutable. The causes, cloaked for millennia in darkness, are now coming under scientific scrutiny. Teams are racing to analyze the clues: deep boreholes, subtle shifts in the land, satellite radar that can detect the tiniest heave. Some researchers now advance the hypothesis that beneath the gorge, a hidden pulse of magma is at work, slowly inflating and subtly reshaping the surface. But what does this mean for the millions who explore these trails, nurture communities in the region, or depend on the Columbia's bounty? Are we merely witnessing the next beat in Earth's immense geological cadence, or is a more profound and potentially hazardous change underway? What, in truth, lies beneath the Columbia River Gorge, and what might today's changes portend for the future? The evidence revealed a landscape in motion. The story did not begin with fire or thunder, but rather with an accumulation of quiet data, sheets of figures, false color maps, and modeled terrain, all compiled from terrestrial surveys and satellite observations. Over 6 years, collaborative scientific teams drew from an unprecedented range of sources: dense GPS networks, geophysical scans, forest inventory surveys, and repeated passes from Earth-sensing satellites. Their detailed measurements converged. GPS stations anchored deep in solid basalt registered minute, gradually increasing uplift, bare millimeters each year, yet trending inexorably upward. More dramatically, INSAR, interferometric synthetic aperture radar, collected by satellites, detected specific ripples in the land surface, regional swells, and arc-shaped rises, their patterns overlaying the gorge's most rugged heart. Seeking explanations, the researchers examined every likely cause. Had the Earth rebounded from the colossal floods of Lake Missoula, whose ancient pulses could have pushed, then relieved, untold tons of pressure from the land? Or were the granite bones of the gorge flexing under the vast, slow collisions of tectonic plates? When current motion data was layered atop long-term topography and mapped against known faults, neither explanation proved sufficient. Instead, the uplift radiated out from below with an arch-like pattern that seemed neither random nor uniform, but structured, tracing areas of the most ancient and dynamic geology. Correlations between present ground movement and prehistoric volcanic eruption zones began to emerge. Where the Earth bulges now are the very spots where fire and rock once reshaped the landscape tens of thousands of years ago. Beyond simple elevation, soil moisture records, local water table fluctuations, and observations of minor spring and gas emission events offered further evidence of ongoing changes at depth. Monitored across seasons and years, the data painted an increasingly clear picture. The land beneath the gorge is in motion, behaving more like a living organism than a static monument. The question then became not whether uplift was real, but what force was driving it from below. The case for magmatic inflation. As multiple lines of evidence accumulated, a provocative hypothesis took shape among the research community. The measured uplift shows hallmarks of magmatic inflation, a subterranean influx of molten rock exerting upward pressure on the crust. This idea, while bold, rests on patterns familiar from other volcanic and geologically active regions across the world. Historically, the gorge has not presented itself as an active volcanic area. Its famous basalt flows originated from fissure eruptions far east of the Cascade Range millions of years ago, but the present uplift could not be straightforwardly tied to those ancient events, nor to the subduction processes that fuel the Cascade volcanoes. Instead, close inspection of the current uplift arch traced it along ancient faults and volcanic structures, places where fractures and weakened rock form possible pathways upward. Deep geophysical monitoring, utilizing seismic reflection and resistivity studies, registered shifts in the way energy travels through selected regions, subtle but suggestive of altered rock, potentially from exposure to high temperatures or injected fluids at depth. These anomalies, though not conclusive proof of current magmatic activity, support the concept that ongoing processes in the mantle or lower crust might be flexing the rocks above. Notably, the uplift's spatial variation, rising more on one side, arching asymmetrically, matches models for magma accumulating in irregular, pre-existing fracture zones rather than simple surface rebound. In some areas, geophysical logs recorded lower electrical resistivity, another potential fingerprint of partial melt or hot, brine-saturated rock. While researchers point out that the magnitude and rate of uplift are modest, the pattern is persistent and distinct, challenging long-held assumptions about the gorge's current stability. The cautious consensus, magmatic processes may be slowly contributing to the uplift of this part of the Columbia River Gorge, not as a harbinger of imminent eruption, but as a reminder that the gorge is geologically alive. Satellites and sensors watching the invisible. To increase confidence in these interpretations, research teams have harnessed the power of modern monitoring, the great advantage of the space age. Satellites, looping the Earth in regular cycles, gather data both day and night regardless of weather, creating surface displacement images with millimeter sensitivity. Season after season, their records reveal that the pattern of uplift is far from transient or coincidental. It is an ongoing process with seasonal fluctuations, yet trending steadily higher in cumulative effect. Networks of precision GPS units, seismometers, and borehole tilt meters installed along the gorge and beyond offer ground truth for the satellite's bird's eye view. The ground is moving, rising more quickly in some zones, slowing in others, but never reverting to a static equilibrium. Forest survey data, primarily gathered by the Pacific Northwest Research Station for other purposes, has been reanalyzed to cross-check for corresponding changes in canopy structure and soil depth, with results indicating subtle but real shifts over time. Seismic arrays contribute a different line of sight, recording swarms of small, unfelt tremors. These may not be dangerous in themselves, but their timing and distribution hint at slow fracturing or fluid movement deep underground. When plotted against the time series of measured uplift, these tremor swarms tend to coincide with growth phases in the deformation arch, suggesting a relationship consistent with slow, magmatic, or hydrothermal movement. Repeated campaigns of ground-based measurement confirm that the process is ongoing and not simply the fading echo of ancient events. Yet periods of quiescence, pauses in the rise, also appear in the record, sometimes presaging a secondary surge in uplift weeks or months later. While it remains uncertain whether these pauses and spurts signal the episodic arrival of new magma, analogous patterns have been observed in other volcanic regions prior to renewed activity. Scientists remain vigilant, tracking each change through dense data networks. The work is far from finished, but each new season's observations reinforce the growing realization: the land here is not at rest. Clues etched in stone, the volcanic legacy. Evidence of ongoing transformation is not limited to the data of the present. Cores drilled deep into the gorge's flanks tell their own, older story, preserved in ancient ash layers, pockets of altered clay, and mineralized fractures. Analysis at the microscopic and chemical level reveals zones of rock that have been subjected to unusual heat and fluid flow, hallmarks of magmatic activity. Mineralogical surveys identify clays and alteration minerals, such as montmorillonite, elite, and zeolites that require sustained thermal water percolation or past hydrothermal systems. Chemical traces of lithium, boron, and rare earth elements in some layers further suggest past interaction with hot magmatic fluids rather than the colder, more uniform groundwater flow expected in stable volcanic deposits. Isotope analyses of oxygen and hydrogen in rock samples stand out from the regional background, aligning with geochemical profiles seen near known magmatic centers. These findings point to a legacy of repeated heating events consistent with uplift episodes but do not confirm their recurrence in the present. Still, the overlap between today's areas of maximum uplift and those with the most striking mineralogical signatures is notable. Field surveys reveal fault slickensides and microfractures, physical proof of the shifting, arching forces that have shaped the gorge in the distant and somewhat recent past. This convergence of geological and geophysical evidence underscores an important truth. The Columbia River Gorge is the product of both ancient volcanic violence and continued crustal instability, and the two are likely more connected than has been believed. Landslides and instability. The surface reacts. Where the Earth moves below, its effects will eventually break through to the surface, sometimes suddenly. Landslides in the gorge, such as the large mass movement documented near Rock Creek west of Stevenson, offer stark reminders of this ongoing instability. These features are not new to the gorge. Indeed, the region's extreme topography owes much to periodic slope failures and mass wasting. However, recent mapping has found that many of the largest, most active slide zones overlap with areas of recent measurable uplift. The logic follows. As the ground beneath swells, however imperceptibly, the strong but brittle basalt layers and their weaker sedimentary caps become stressed in new directions, increasing the likelihood of slope failure. Even minor bulges or subsidence at depth can upset a delicate balance, causing thousands of tons of rock and earth to shift downslope. Hazard mapping, now updated through regional natural hazard mitigation planning, some funded by the Federal Emergency Management Agency, FEMA, is beginning to reflect these changing realities. Planners and engineers account not only for river flooding or earthquake risk, but for the ongoing instability that comes with land in dynamic motion. Residents, too, notice firsthand evidence. Shifts in the depth of wells or the sudden appearance of cracks and minor slides along highways and trails highlight the practical consequences of invisible changes at depth. Ecologists monitoring vegetation note how subsurface movement affects drainage patterns, sediment supply, and sometimes even the survival of sensitive plant species. The frequency and scale of landslides in the last few decades may be accelerated by, or at least correlated with, these broad, subtle movements in the deeper geology. As uplift continues, the prospect of more widespread instability remains a serious concern. Forests, fires, and chain reactions in the ecosystem. The Columbia River Gorge is not just a geologic wonder, but an ecological tapestry. Its forests, meadows, and wetlands exist in finely tuned balance. Where the Earth moves most, that balance is most at risk. Forest inventory data, extending over years, show that tree growth, root structure, and species competition are altered where the ground uplifts substantially or slides away. Root stress, caused by twisting and heaving soils, can lead to reduced tree vigor and increased susceptibility to pests. Incipient landslides may uproot entire groves or change the course of creeks, with cascading effects on fish, amphibians, and birds. Although recent catastrophic fires have occurred elsewhere, no AA notably tracked a major wildfire in Ocean County, New Jersey. In 2025, the Pacific Northwest remains acutely aware of its own vulnerability to fire, especially where landslides clear swaths of forest or shift wind patterns, where ground movement alters drainage or exposes exposes new slopes, the risk of subsequent fire events can rise, making the gorge's ecosystem doubly exposed. Native plants, such as Oregon grape, sword fern, and Douglas fir, sometimes struggle in the shifting soils and changing hydrology linked to uplift. Subtle changes in water table elevation or soil compaction can spell the end for less resilient species. Field botanists have observed the disappearance of rare wildflowers and shallow-rooted species from areas experiencing either rapid heaving or repeated surface fractures. For the public, the most visible sign may be in disrupted trails, unseasonal wet spots, or occasional bursts of spring activity where none was expected. Trail realignments, increased maintenance, and the sudden appearance of perched water or new seeps hint at deeper changes at work. As the landscape evolves, so too do its biological inhabitants, some thriving in disturbance, others disappearing. The net ecological impact is complex, but the message is clear. The rhythm of geological change echoes throughout the living web. A corridor of giants, context in deep time. Widening the view beyond the gorge, we see it as part of a vast corridor of volcanic landscapes stretching across the western United States. The Columbia River Gorge is a scar, a unique incision within the much larger framework of the Columbia River flood basalts and the Cascade volcanic arc. It lies at the intersection of enormous magmatic provinces where the Earth has reshaped itself over millions of years through both explosive and effusive events. The basalt flows underpinning the gorge were laid down by colossal prehistoric eruptions, blanketing much of what is now Washington, Oregon, and Idaho. Over time, other, more familiar volcanoes, Mount Hood, Mount St. Helens, Mount Adams, rose to prominence nearby, marking the ongoing tension along the Cascadia subduction zone. Satellite and gravimetric measurements suggest that, throughout this corridor, invisible changes continue. Pockets of low crustal density, seismic anomalies, and periodic ground deformation are observed not only at known volcanoes, but also in quiet regions like the gorge itself. Geological mapping confirms that the area is crisscrossed by faults and fissures, marking a history of repeated deformation stretching back before the last ice age. Some of these structures act as corridors for deep fluids and occasionally magma movement. Seen in the light of deep time, today's slow uplift may be one more pulse in a much longer cycle, one that has, in the past, resulted in dramatic landscape-altering events. There is no certainty it will do so again in our lifetimes, but the precedent is set in stone. Waiting on the edge, unanswered questions, uncertain ground. The Columbia River Gorge today stands poised between tranquility and transformation, its cliffs, forests, and valleys inscribed with the marks of ancient and ongoing change. Scientists strive to forecast what might come, leveraging the best tools of our era, vast sensor networks, Earth-observing constellations, and the analytical power to draw meaning from millions of data points. Continuous monitoring promises rapid detection of new developments. If uplift trends accelerate, if a swarm of micro-earthquakes occurs, or if shifts in groundwater chemistry arise, regional teams are prepared to react and to inform the public, with hazard plans now accounting for dynamic ground movement as well as the more familiar dangers of flood or fire. Communities are better equipped than ever before, but enormous questions remain. Will uplift in the gorge continue and then fade, as has likely happened innumerable times over geologic history? Or are we seeing early signals of a more significant rejuvenation of underlying magmatic systems? For now, the answers remain uncertain. On the surface, life continues, much as it always has. Hikers still gaze in awe from cliffside viewpoints. Kayakers trace the river's winding path, and wildlife forages in the same forests that have endured centuries of change. To those above, the land feels solid, eternal. Yet the invisible movements beneath, captured by satellites and ground instruments, tell a story of constant flux, a landscape still being written with every passing year. Is this uplift the quiet prelude to something larger, or simply another passage in the ongoing story of Earth's ever-changing face? Data will tell with time. In the meantime, the Columbia River Gorge reminds us all that even the most ancient landscapes are alive with possibility and motion. Stay attentive to the latest findings as science continues to illuminate the mysteries beneath the gorge. Subscribe for ongoing updates as satellites and researchers work to decode this captivating fascinating region. Is this just one more turn in the river's tale, or the preface to a yet unimagined change? Thank you for joining this journey through science and time. And remember, every landscape, no matter how old or grand, still adds to its story, one silent inch at a time.